Right now, I mean, tech companies are pouring just billions into artificial intelligence that can, write flawless software code or pass the bar exam or...
Generate hyper-realistic video from
Yeah.
like a simple text prompt.
Exactly. But if you take that exact same billion-dollar technology and put it on the floor of a chemical manufacturing plant, a slight shift in the room's humidity or like a tiny variation in a raw material can cause the whole system to just completely crash.
Oh yeah, it just hits a wall.
Welcome to the Deep Dive. Today, you and I are exploring a fascinating and honestly largely hidden problem in the tech and manufacturing world. We're looking at why artificial intelligence is hitting this massive solid brick wall when it tries to move out of the, pristine R&D lab and onto the actual messy factory floor.
It is a phenomenal bottleneck.
Yeah.
And it fundamentally challenges the narrative we usually hear about AI being this omnipotent plug-and-play solution. Because we are looking at a space where the digital world is just absolutely forced to reckon with the chaotic physics of the real world.
Yeah, right. And to understand how industry insiders are desperately trying to fix this, we've got our hands on the syllabus and the detailed course materials for a $199 online training program. It's offered by a group called OnlyTRAININGS, and the course is titled AI in Chemical Industry 2.0, Execution, Deployment, and Real-World Integration.
Which, I mean, that might sound incredibly niche to some people listening.
Yeah, it sounds a little dry.
It does. But it serves as a perfect microcosm for the limits of modern technology.
Okay, so let's unpack this, because the core thesis of this training program is essentially a wake-up call to the tech industry. They're arguing that building the actual AI model, writing the code, setting up the neural network, is just no longer the bottleneck.
Right. The coding part is relatively easy now.
Exactly. The real challenge, the thing causing a huge number of AI initiatives to just fail, is surviving the physical reality of chemical execution. I mean, R&D teams, formulators, process engineers, they already know how to use AI for prediction and optimization in the lab.
They've been doing it for a while.
Yeah. But when they try to get those same consistent results in actual production, the whole thing just stalls out after the pilot phase.
The course materials actually refer to this as the implementation gap.
Yeah.
You have these pilot projects that look brilliant, like absolutely flawless on a computer screen.
Right.
But they collapse when exposed to real-world operational constraints.
Mm-hmm.
To understand why, you really have to look at the fundamental difference between, manipulating data and manipulating actual physical matter.
I was trying to visualize this gap, and my mind, it immediately went to food. Because, yeah, imagine you're a world-class pastry chef, right? And you've developed a recipe for just the most delicate, perfect souffle. You're in a pristine test kitchen. The climate is perfectly controlled. You're using a highly calibrated digital scale to measure your flour down to the, the milligram.
Uh-huh.
The ambient humidity is locked at exactly 42%, and your oven has absolutely zero temperature fluctuations. So in that lab, your recipe works perfectly every single time.
Sure, but taking that recipe to a massive industrial facility changes the entire paradigm.
Yes, because now you have to execute that exact same recipe in a massive industrial bakery that's producing 10,000 loaves a day. The floor is vibrating constantly from the heavy machinery. The massive oven doors are constantly opening and closing, which is causing wild temperature swings.
Oh, the draft salon, yeah.
Exactly. The flour you got from your supplier today has a slightly different moisture content than the flour you got yesterday. Suddenly, your perfect test kitchen recipe, which is our brilliant AI model here, completely falls apart.
Yeah, and take that bakery analogy just a step further to really capture the chemical industry's reality. Because it's not just that your bread is going to fall flat.
Right, the stakes are higher.
Way higher. Not only is the floor vibrating and the temperature swinging, but in a chemical plant, if that oven temperature swings too high, your product doesn't just burn. It might become highly pressurized, trigger a runaway exothermic reaction, and create a massive toxic hazard.
Wow. Yeah, that's a whole different ballgame.
The stakes are intensely physical and immediate. And the syllabus highlights these specific physical constraints, right? They mention severe batch variation, raw material shifts, and multi-factor interactions that are almost never captured in a controlled pilot project dataset.
When we talk about multi-factor interactions, my mind immediately goes to how a tiny change in one raw material might, I don't know, cascade down the line. Is that what is really tripping up the algorithms?
That is exactly the core of the physical constraint problem. I mean, think about batch variation. The purity of a resin or a solvent might vary by just a fraction of a percent from one delivery to the next.
Okay.
In an R&D lab, an engineer is using the same tiny, highly controlled bottle of chemicals for all their tests. But on the plant floor, you are dealing with thousands of gallons being pumped from massive rail cars.
Oh, wow. Yeah.
Those slight raw material shifts interact with other variables like the ambient temperature of the factory or the sheer mechanical force of a giant industrial mixing blade in ways that cascade totally unpredictably.
And the AI model, which was, trained on data from the pristine pest kitchen, has absolutely no idea what to do when that cascade happens. It hasn't seen the vibrations or the humidity or the mechanical shear force.
It hasn't seen any of it. Nor does it understand the interconnected safety limits of a giant chemical reactor. Chemical operations are fundamentally more complex than standard data projects.
Because the consequences are physical.
Exactly. If an AI miscalculates a movie recommendation, the worst outcome is a bored viewer. If an AI miscalculates a chemical process, you're dealing with pressure thresholds, safety valves, and massive financial losses from completely ruined batches.
Right.
The physical environment is completely different, which means the structure of the information itself breaks down when you move from the lab to the floor.
Wait, hold on. I need to push back on that a little bit. Because doesn't artificial intelligence thrive on massive amounts of data? I mean, the chemical industry has been recording sensor data for decades, right?
Oh, absolutely.
Temperatures, pressures, flow rates, all of it. Shouldn't that massive volume of factory floor data be enough for the AI to learn those multi-factor interactions and just, get smarter over time? My instinct would be to just feed the model more of that plant data.
Yeah, and that assumption is exactly why so many of these projects fail. The course materials actually dedicate a significant amount of time to completely dismantling that idea. Yeah, it comes down to understanding the difference between noise and signal in chemical data sets. Yes, the industry possesses mountains of data, but that data is incredibly fragmented.
Fragmented how?
Well, it exists across entirely different operational silos. You have lab trials over here, you have quality control systems over there, and then you have the continuous plant operations data somewhere else entirely.
So they aren't integrated. The systems just aren't talking to each other.
It's more severe than just a lack of communication. They are speaking fundamentally different languages. The data is inconsistent and completely disconnected from how decisions are actually made on the floor. When an AI data scientist looks at a massive data set, they assume all that data is a reliable signal that the algorithm can learn from. But in reality, a huge portion of it is just noise, created by what the course calls scale-up distortions.
Okay, I want to dig into that term. What exactly is a scale-up distortion in this context? Because I hear scale-up and I just think make it bigger. How does the physics actually change just by making something larger?
Well, let's look at the thermodynamics of scaling up a reaction. Imagine a chemical reaction happening inside a 1-liter glass flask in a laboratory. That flask has a very high surface area to volume ratio, meaning heat can escape through the glass very quickly. The reaction might take, say, 10 minutes to cool down.
Makes sense.
Now, move that exact same chemical reaction into a 10,000-liter stainless steel reactor on the plant floor. That massive reactor is essentially a giant thermal sink. The surface area to volume ratio has absolutely plummeted.
Oh, the heat has nowhere to go. So a reaction that cooled in 10 minutes in the lab might take, 4 hours to cool in the plant?
Precisely. That thermodynamic shift is a scale-up distortion. Now, consider the AI model. If the algorithm was trained entirely on those clean, 1-liter lab datasets, its internal map of thermal decay is just completely wrong for the factory floor.
Because it thinks it takes 10 minutes.
Right. So it will make predictions that severely violate the operational limits, what engineers call the boundary conditions of the real plant. The AI might confidently tell the human operator to, increase the temperature by 10 degrees right now to optimize the chemical yield, because that timing worked perfectly in the simulated lab data.
But the human operator knows that injecting more heat into 10,000 liters of an already insulating fluid will cause a massive, dangerous pressure spike.
Exactly. The operator recognizes it as a physically impossible command. If the AI's training data doesn't reflect the real-world scale-up physics, the batch variation, and the actual boundary condition limits of the machinery, The model's predictions are worse than useless.
They're dangerous.
Yeah, and the companies funding these projects quickly realize their very expensive AI is basically hallucinating solutions that violate the fundamental laws of physical chemistry at scale.
Okay, but identifying that you have fragmented, noisy data that hallucinates scale-up distortions is one thing, right? Recognizing the problem is only half the battle. The real question is how engineers are supposed to actually fix this. Like, how do you use this technology to actively solve problems on the fly instead of just generating these dangerous suggestions?
Well, the curriculum addresses this by shifting the entire approach to experimentation. It moves away from the idea of just throwing more big data at a deep learning model and instead focuses on actively mapping the boundaries of the process.
Here's where it gets really interesting, because the solution they focus on isn't just like a software patch or a better algorithm. I want to highlight a very specific detail about the creators of this course, OnlyTRAININGS.
Yeah, their background is key here.
It really is. They make a massive point in their marketing of stating that they are active industry professionals, they are not academic theorists, and they're definitely not generalist Silicon Valley software developers.
They place a very heavy emphasis on that battle-hardened perspective. They explicitly state they have sat at the same lab benches, faced the same scale-up failures, and navigated the exact same intense regulatory pressures as the chemical engineers who were taking their course.
Yeah, they list backgrounds in polymer science, coatings technology, cosmetic formulations, and adhesives. So because they have actually felt the pain of a 10,000-liter batch failing, their solution completely shifts the focus.
Right.
They aren't trying to build a magical algorithm that runs the whole factory. They focus on concepts like multivariable failure mapping and predictive defect identification.
Which represents a completely different operational paradigm. Instead of asking the artificial intelligence to perfectly optimize a golden batch from start to finish, which, as we know, it can't do because of those scale-up distortions, you use the AI to map out exactly how and why a batch is going to fail. You use it for failure analysis and root cause detection.
Okay, so going back to our industrial bakery analogy, instead of the AI acting as the master chef trying to perfectly bake the bread, it acts as a hyper-vigilant inspector. It constantly scans the ambient humidity, the incoming flour moisture, and the oven temperature swings to say, hey, based on how these three variables are interacting right now, your bread is going to collapse in exactly 12 minutes unless you adjust the yeast.
That captures the essence of it perfectly. And to achieve that kind of failure mapping, the course outlines a methodology called AI-assisted experimentation, specifically focusing on AI-guided DOE, which stands for Design of Experiments.
When I hear design of experiments, my mind just jumps to a computer running a million virtual simulations to find the best outcome. Is that what AI-guided DOE is?
Actually, no, it's almost the exact opposite.
Oh.
Because running a million virtual simulations is exactly what fails. The simulation is usually based on that flawed lab data we talked about.
Right.
Traditional human experimentation involves changing one variable at a time.
Yeah.
You change the heat, test it, then you change the mixing speed, test it. It's incredibly slow. DOE is a statistical approach where you change multiple variables simultaneously to understand how they interact with each other.
But the combinations must be endless.
They are, which is why AI-guided DOE is so powerful. The AI isn't simulating the chemistry. It is optimizing the experimental matrix.
Oh, I see.
The algorithm suggests the absolute most efficient set of physical, real-world experiments for the human engineer to run in order to map the boundaries of the process. It reduces the R&D cycles drastically without relying on full automation.
Because humans are still doing the physical work.
Exactly. It respects the physical reality because humans are still running the physical tests, but the AI is telling them exactly where to look for the failure points.
I imagine that means you need a very specific kind of organizational structure to pull this off. Like, you can't just have an incredibly smart data scientist walk into a chemical plant, look at a spreadsheet, and figure this out.
It is entirely impossible in isolation. The course insists on the absolute necessity of building hybrid domain plus AI teams. Artificial intelligence simply cannot function as an isolated IT project in the chemical sector.
It needs the chemists.
Yes. It requires people with deep domain expertise. The polymer scientists, the cosmetics formulators, the process engineers, to bridge the gap between the formulation science and the digital code.
Because I guess the data scientists might see a numerical anomaly in the sensor data and just try to smooth it out mathematically, whereas the polymer scientist looks at that exact same anomaly and says, no, wait, that data point means the polymer chain is degrading under sheer stress.
Exactly. The domain expert provides the physical context that the data scientist lacks. The data scientist knows how to tune the neural network, but only the chemical engineer knows what an actionable process parameter actually is for that specific piece of machinery.
Yeah.
You have to merge the people who understand the code with the people who understand the chemistry. They have to work in tandem to translate digital predictions into actual physical actions.
But even if a company manages to do all of that, I mean, even if they build a highly functional hybrid team, utilize AI-guided DOE, map all their multivariable failures, and build a model that actually respects the scale-up physics, that model still has to survive the bureaucratic and technical red tape of the industry.
Oh, yeah. The red tape is a formidable barrier. It is where many theoretically sound technical ideas go to die.
Yeah, the final modules of this curriculum dug deep into the hurdles of deployment. Specifically, integration, reliability, and being audit-ready. The source materials list some pretty heavy enterprise systems that the AI has to successfully integrate with. Things like LIMS, MES, and ERP.
Right. And for listeners outside of the manufacturing software space, LIMS is a laboratory information management system, so it basically tracks the quality control tests.
Got it.
MES is a manufacturing execution system. That's software controlling the actual machines on the plant floor. And ERP is enterprise resource planning, the business software handling inventory and raw material purchasing.
Which means the AI has to simultaneously ingest data from the lab software, the factory floor machinery, and the business inventory software. I can see why that's a total nightmare.
It's incredibly complex.
Because, the lab software is logging a discrete quality test taken at 2 in the afternoon, while the floor machinery is logging continuous, chaotic temperature readings every single millisecond. Trying to map a single discrete lab result to a massive wave of continuous time series data it sounds almost impossible.
It is a massive data architecture challenge. And beyond just getting the systems to talk to each other, the AI has to function while being strictly audit ready.
That specific phrase stood out to me. Is making an AI audit ready just like a bureaucratic hoop to jump through for government regulators? Or does it actually serve a technical purpose? Does it make the AI itself a better tool?
It fundamentally forces the AI to be a better, more robust tool.
Yeah.
In highly regulated environments, audit ready is essentially synonymous with what the course defines as decision grade. Consider the context here. The OnlyTRAININGS experts specifically note their experience navigating EU and FDA compliances. If an artificial intelligence recommends a sudden temperature change for an FDA-regulated pharmaceutical coating or a structural adhesive used in automotive manufacturing, you cannot just tell an auditor, well, the black box algorithm told us to do it.
Because the algorithm can't be cross-examined. A black box neural network just spits out an answer based on millions of hidden correlations, but it can't explain its own logic.
And correlation is just not enough in a regulatory audit. You must prove causation.
Right.
Trust is impossible if the hybrid teams cannot trace the AI's predictions back to the original process behavior, the operational risk, and the practical constraints of the machinery. Being audit-ready forces the development of explainable AI.
It forces them to show their work.
Exactly. It forces traceability and comprehensive documentation. It ensures that the model's reliability is constantly being checked against actual operational risk rather than just raw mathematical accuracy.
So the bureaucracy actually acts as a tether, kind of grounding the AI in physical reality. It forces the developers to say, hey, we can't just rely on this hidden correlation. We have to mathematically prove the causation and document it so a human inspector can actually understand it.
By forcing the AI to be decision grade and mapped to physical failure points, companies establish a framework for what is actually deployable today versus what is just industry hype.
Yeah.
They start chasing the fantasy of a fully autonomous AL-run chemical plant and start deploying practical, highly reliable tools that assist human engineers in making complex formulation decisions.
So what does this all mean? If we synthesize everything we've pulled from this OnlyTRAINING syllabus today, the real takeaway for you, whether you work directly in the chemical industry or you're just someone who wants to understand the actual limits of modern technology, is that execution is everything.
An idea or predictive model is really only as valuable as its ability to survive messy, real-world constraints.
It has to be trusted by the humans actually turning the valves, running the audits, and managing the risk. If an AI model cannot survive the transition from the pristine, climate-controlled test kitchen to the noisy, vibrating industrial bakery, it isn't a revolutionary tool. It's just a very expensive, highly sophisticated science experiment.
The gap between digital simulation and physical reality remains incredibly wide, and bridging it requires deep human expertise, not just more processing power.
Which leaves us with a lingering, somewhat provocative thought to mull over. We've spent this entire deep dive looking at how our most advanced, state-of-the-art predictive algorithms are constantly being humbled by the simple, chaotic physical variables of a manufacturing plant.
A slight temperature shift.
Right. A tiny variation in the moisture of a raw material. If our absolute best models are continually struggling with the basic physics of a chemical reactor, does that mean the ultimate bottleneck for the future of artificial intelligence isn't a lack of computational power or a shortage of microchips? Is the real ceiling on AI simply our inherent human inability to perfectly digitize the messy, vibrating, chaotic physical world?
It raises the possibility that the physical world is fundamentally too noisy to ever be perfectly contained inside a pristine digital box.
Something to think about the next time you hear a headline claiming an algorithm is about to automate the entire physical world. It still has to figure out how to survive the factory floor first. Thanks for joining us on this deep dive. We'll catch you next time.